In the next couple sections, we're going to spend a lot of time learning how to find the volume of three-dimensional objects. Now, these are going to be three-dimensional objects that are different than the geometric ones that we know from geometry class, such as cylinders or cubes. Those are relatively easy. I mean, there's a reason that the ancient Greeks 2,000 years ago knew how to do this, 2,500 years ago. All right, so we want to be able to find the volumes of three-dimensional objects. And let me tell you a little story about Johannes Kepler. So Johannes Kepler had a lot of children, and he was married a couple times. And at his second wedding, he had to buy a wine barrel. And he was displeased with the method of finding the volume of wine from a wine barrel because it's not a perfectly cylindrical shape, right? And he didn't like what the merchants were charging him for it, and he felt that he was getting fleeced, and he wanted to mathematically figure out the volume of a wine barrel. And you can see this is Kepler's original drawing about this problem and his barrel drawing, right? So this is a problem that dates back to the 1600s, if not earlier, because for as long as humans have been around, we've been creating things that form different shapes, but are centered around an axis, which is what we're particularly interested in. Things that are found by rotating around an axis. For example, what if you had a vase like this, right? This is blown glass, but what's the volume of it? Right? It doesn't fit the standard geometry rules of cylinder or sphere or a rectangular prism. Those we know. Those are easy. But how do I do this? Right? Well, I can see there's an axis going down the middle, right? It goes right down the center, which is where the glass is blown from, right? So there's an axis down the center. So if I could just figure out what the curve was, then maybe that would help. Or, better yet, a more personal, that particular one I bought in Venice, actually. This one is made for me by my brother. My brother's actually quite good with clay, and he has thrown many, many, many pots. And so what you do is you have a big wheel, a pottery wheel, and you take a piece of clay and you pull up as the pottery wheel spins around. It spins, and then you use your thumbs and your fingers and your pressure, and you pull up on the clay, and you make a clay pot, right? So this one my brother made for me. Isn't that nice? But it's also for other things besides just clay pots and glass. For example, the humble potato. Now, I did my best to slice this because this is the first method we're going to look at, which is the general slicing method. So you're going to imagine an object, right? And then you're going to imagine slicing it. All right, we'll come back for you, potato. That's the best I could do. I didn't have any zucchini in my house. So as you can see, zucchini, party decorations, planets, because planets are not perfect spheres. How do we find the volumes of them? We could use this method. Also, anything that's made on a lathe. Now, clay pots are not made on a lathe, but let me show you what a lathe looks like. They're big pieces of machinery. I happen to know somebody who owns one. It's very large, not this large. This is industrial scale down there. But you can see this person, what you do is you take a block of wood and it spins it around an axis, and then you use tools like this person's using the tool to kind of grind down parts of that wood and make it smooth and lovely. That's how you can make wooden bowls, right? So that's a lathe. So anything that you'd make on a lathe, anything that you'd make on a pottery wheel, so or anything kind of blown glass, if it's symmetrical, you can use this for it. So this has been a problem for a long time. So barrels would also be another one. Kepler would be proud. Barrels, vases, right? Like the vase that my brother made me, that kind of thing. Those would also be examples of things that we could use these methods to find the volume of. So this is a mathematical problem that's been around for a while, and we're going to spend a couple sections learning how to do it. And then we're going to expand and learn how to find the surface area of these objects as well. More on that in a later section. All right, so let's go back to my potato. Because what you have is you have an object and you're cutting across it, right? And so when you cut across it, you create an object. Now, like in this particular one, it's a parabola shape, right? But in my particular potato, and my room smells like potatoes here, right? It's kind of an oval shape, right? So if I cut this open, that's an oval, sort of, right? Kind of an elliptical shape. Okay, so if I can stack them all up, if I can cut, and then you can imagine where I'm going with this. Much like with Riemann sums, we don't just want it to be this finite number of cuts. We want infinitely many cuts. We want to slice finer and finer and finer. If we can do that, if we can slice it finer and finer and finer, then we could add up all the areas of all of these surfaces, right? So instead of taking the volume of a disk like this, we would, well, you take the volume of the disk, but you take it to be infinitesimally thin. So a really thin disk, and you add, and you stack them up. You add up all the slices. And that's what you're going to do, right? You're going to add up all your slices, but since you're going to add up infinitely many slices, what you're really going to do is take the integral. Now let me show you just a couple other things really quickly. One, here it is, just an image of what's happening on our particular problem, because of course you're letting the number of slices n get larger. It's going to make the thickness get smaller. Now I could not actually go that thick. I'm not a professional chef, so my thickness of my slices are pretty wide. I would say that I'm more in this top right corner of thickness slicing for my potato. But let's say if I was a sushi chef with a very sharp knife, I might be able to get more like that bottom left corner, right? That one with lots of slices in there. But of course, that's not infinitely many. Infinitely many would be the smooth surface itself. Kepler, by the way, predates Newton, so he was not actually able to do this calculation perfectly because he didn't have integrals. Kepler was alive and dead before Newton. I believe he died before Newton. Well, very least before Newton published. So he was done and never really got the solution to his problem for his wine barrel. So it's fascinating, but he spurred conversations, let's put it that way. And he was very frustrated with his wine barrel purchase. Just so you know, you can look at cross sections of all sorts of things. Now, this cross section was a parabola. The previous cross section was a oval for my potato, but I actually have some pictures for you. That's what I'm pulling up, if I can grab them. There. All right, so I can make it so that the cross sections are squares, and that would create an object. Or the cross sections are, let's see what they are here, rectangles. Right? Now, not the whole thing is not drawn here, but you're getting kind of an image of what it would look like. Or I can make the whole cross sections semicircles. Looks like a fish to me, right? But there's an object kind of over the top of this. So you can have different cross sections and they can do different things. This particular one has a triangular cross section. Right? So we can cross with a lot of things. And this means that we could find things not just for a vase, right, which is a pretty easy thing to do, all things considered, because every cross section on my vase is going to be a circle. So that's going to be relatively easy. But what if it was my potato? What if it wasn't as easy? What if it was triangular when I cut into it? Or what if it was a square when I cut into it? You could still do it. As a matter of fact, I have another weird object here. I have a deck of cards that I bought that are terrible to play with. I would not recommend it. But every cross section is this weird kind of, it's not an oval because it's got these straight sides. So, but nevertheless, if I stack up the infinitely many, well, they're not infinite, but they're getting very thin, and I stack them, I would have the volume of this object, right? So when I cut into it cross-section wise, it's like this. Okay? And that's the theory behind what we're doing for the next two sections. Well, actually for this section in particular. This section is all about slicing. So we're going to cut into these objects. So imagine my potato, and you cut finer and finer and finer. You're going to let n go to infinity, n being the number of slices. So if you're going to have infinitely many slices, then what you're really talking about is an integral. So when we learned that in Calc 1, right, that's what Riemann sums are all about. Riemann sums are a two-dimensional version of this. This is a three-dimensional version. So you're stacking up slices instead of just stacking up rectangles. All right, so that leads us to the general slicing method. Now, this method works no matter what. This method works also, by the way, if it's dy. It's written as if it's dx. So you can see down here a of x and dx, a to b. But that's just convenience. We just don't write both versions because there's no point. So it works the same way for dy if it's more convenient for whatever reason to do a version with dy. So you have a beginning point and an ending point. This is x equals a, and of course it's x equals because it's dx over here. And then this is x equals b. Now, if you were doing dy, then those would be y values. Y equals a, y equals b. You have your cross-sectional surface area. So in my case with the potato, it's that area of that oval bit, right? So that's your cross-sectional area right there. And if in the case of the deck of cards, it's whatever the area of this one card is, whatever that may be. Okay? In the case of the vase, it would be a circle, right? Because you're cutting across it. And when you cut across it, you're going to have a circle, right? Right there. So that's the circle that's at the bottom, right? But you can see that all along this thing, because it's so beautifully blown in Venice, that its cross sections are all circles. Okay. So it'll have a cross section of whatever it has, and that cross sectional area, you will multiply it by the thickness of your slice, which will get infinitesimally thin, even thinner than those cards in that deck of cards. So you'll go from x equals a to x equals b. You'll multiply area times thickness, which gets you the volume of the slice. So when you take the area of this card times the infinitesimal thickness of this card, you actually have the volume of the card, and then you stack up the cards from the beginning to the end.